Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
There we are.
There we are.
We are. I always try to make that as seamless as possible, and it's like I'm trying to make, you got to be like one of those producers of like fancy shows, right? And it's like it should fade out, and we should be like whoosh, fade right in.
We haven't gotten to that level yet.
Not quite. I think if I click on the tab, you have to like click on things in the right order, and it's like if I click on it early enough, it'll like fade in at just the right moment, and I haven't got it yet. I only get to practice once a week.
That's also
exactly true. Now.
Yeah.
And welcome everybody.
Yes. Welcome to another episode of Ask Us Anything About Electrochemistry. Thank you for tuning in. And we got all the boilerplate stuff out of the way.
Should jump right into it. And one of those is a question that was asked by Isaac just maybe like a half an hour ago or something. So if you are still here, Isaac, hopefully I have your question. Sometimes they disappear on YouTube oddly, like between when we're live and when we're not. So I always check the event just so everybody is aware. If you type a question before the live stream begins, I do save it. So if it disappears in the chat or something like that, it won't go away. In any case, Isaac asked, what causes Warburg impedance to have equal resistive and reactive properties? Is it typical for different electrochemistries to deviate from the 45 degree? And what would a deviation positively or negatively mean? So first, just to be clear, I believe what you're referring to when you say equal resistive and reactive properties is ZR and ZI on the Nyquist plot. I believe that's what you're referring to. So just to be clear, if you are here, Isaac, and you can comment on whether I'm accurate in my assumption, that would be nice. Otherwise, if not, and I've misinterpreted it, then my apologies. But the fundamental feature of the Warburg impedance is this 45 degree line, right, on the Nyquist plot. And so when we say equal, I kind of assume what you mean is like this 45 degree line right here that I'm wiggling around. And now I have to put it back where it came from. Ish there, whatever. It doesn't really matter. Anyway, the point is the X and Y positions. I mean, in this case, it's sort of over to the right more because I have this extra stuff. But you can imagine if it was just from the origin, it's like it would have the same X and Y. It's a slope of 1. It's a 45 degree angle, right? Those are all sort of hallmarks of this feature graphically. And so when you say resistive, that's ZR, like the x-axis, and then reactive. It's not exactly the right terminology in some sense, but I mean, I think you mean the negative imaginary impedance, which is like the phase. It's related to the phase angle, which is a reactive is not a terminology used in impedance, but anyway, that's why I assume that's what you mean. Now, the first answer to your question, however, I've tried to explain the terminology. The first answer is it's just mathematics. Well, I guess there's two answers. One is a phenomenon and one is mathematics. Now, the first answer is just it's mathematics. So the math of a Warburg element is right here. The impedance of a Warburg is equal to a constant divided by j omega to the 0.5 power. And so I'm not going to do the mathematics out here just for time, and you can just hopefully take my word for it. But the point is that when you solve this equation, this is a complex number because it has j, this the square root of -1. When you do the simplification, I guess, or rearrangement to its real and imaginary components, hence the z real, z imaginary, or as you put it, resistive reactive terms, they are identical. Essentially, that's just what happens. Mathematically, it's like square root of 2/2 times W, I think, something like that, basically. But the coefficient of the real and the imaginary terms, when you solve the Warburg impedance, are identical mathematically. So that's just, so they are the same because mathematically that's just how it works out. Now the phenomenon is like, why from a chemistry perspective are they the same? It's a good question. I don't know that I know the answer to that perfectly well. Like something about the impedance of diffusion lends itself to this behavior. I don't know that I can explain that from a phenomenon perspective very well. I might have to think about it a little bit, to be honest. And I don't know that, like, it's very easy to explain, I guess. But the one way that I can kind of explain it, if you will, is to say as a part way as an answer to your last question, which is it typical for different electrochemistries to deviate from the 45 degrees? Yes, it is. And that's why we often use a constant phase element, okay, to represent those features when you have something that is like a Warburg but not quite a Warburg, right? And what I'll do is show one other set of slides to you to hopefully drive this point home. I think it's in this one. Let me find it here, maybe. And this might help answer that last question and, to a certain extent, your first question. CPE. Let me get to a CPE. All right, here it is. So it's the last thing I'll say about this, and then we will move on, is this one here. So you might have to move the question if it's blocking the bottom part. So you can think about this in terms of a constant phase element, right? The impedance of the Warburg that I just showed you was basically where this is 0.5, right? This exponent right here, okay? However, a CPE is where this exponent can be anything. So one interpretation of a Warburg is that it's a constant phase element where the exponent is 0.5. Now consider the other limits. When alpha is equal to 1 of a constant phase element, this is a resistor, okay? I'm going to go over this. I'm sorry. When alpha is 1, it's a capacitor. And when alpha is 0, it's a resistor. Okay. I think what actually might be better is if I use our software. So pardon me just a moment because I know I'm kind of jumping around here, and I'll try to use it to illustrate the point that I'm making. So I'm going to bring up a capacitor, or a CPE really. Okay. So forget about the resistor. I'm going to just minimize it. Pretend this is just a pure capacitor. It basically is. Oh God. Okay. So this is, let's let this be smaller. All right. So here we have a Warburg, like in its pure form, in its pure perfect form. Here, this is a 45-degree line, and the X and Y are equal at all points, right? Now, if you have a slope that's greater than 45 degrees, right? Like this. So it means your alpha is greater than 0.5 of your constant phase element. Or you have it and it's less than 45 degrees. In other words, alpha of a constant phase element is less than 0.5. So this angle with the x-axis is also smaller. Well, what we can do is analyze it in terms of that constant phase element that I was showing you. So first of all, if alpha is 1, it's a 90-degree angle. It's straight up and down. You can't see it. Let me move over. It's straight up and down 90 degrees. Alpha is 1, and it behaves as a perfect capacitor. If alpha is 0, you won't see much. Graphically, it becomes like a point, but you can see. Let me zoom out a little bit here. It gets hard to see. All right. It's like really small. So it's like almost flat. So the angle with the x-axis becomes 0 as I go closer to 0. Okay. And that is behaving exactly like a resistor. So one way to think about the 0.5, the Warburg, is that it is halfway between behaving like a capacitor and a resistor. And so if the angle of 45 degrees, if the angle of the line is greater than 45 degrees, it's closer to behaving like a capacitor. If the angle is less than 45 degrees, it's closer to behaving like a resistor. Okay. Now, again, the tricky part that I always find when I'm trying to explain this is, what does that really look like? Like, what is behaving like a capacitor or what is behaving like a resistor exactly look like? Like, from a phenomenon perspective, it's hard to answer that question. I mean, you could think about a capacitor as two parallel plates separated by some distance with a dielectric in between, oppositely charged. That's kind of our understanding of the inner Helmholtz plane, the double layer, electrical double layer, is kind of fits that description. Now, what happens if one of the plates, which is basically ions, is moving away or towards well, it's like a capacitor still, but it's got a distance that's changing. So it's like a mix of capacitance and diffusion. Maybe that is an explanation of how can something be kind of capacitive, kind of diffusion, right? Maybe that's what you can think about when it's more of a greater than 45-degree angle, right? On the other hand, the resistance, maybe, as you talked about, like it's when you have a tunneling kind of phenomenon with like a heterogeneous rate, electron transfer or homogeneous. Again, I always screw those up. I don't know why. I can't get
homogeneous electron transfer, when it's like
tunneling,
when it tunnels from the electrode to the orbital of the molecule.
Right. So in that case, if you think about the tunneling, that's kind of an electron transfer that's more resistive. So maybe an angle less than 45 degrees and alpha less than 0.5 behaving more like a resistor is some combination of diffusion, but then there's tunneling. It's just a guess, right? I don't know 100%. I don't know anybody that's really explained it. There could be some publications I'm just not aware of, but those are my kind of attempts at explaining what that is. And so electrochemistries that lead to those, like anything that behaves in that manner that I just described, right? I mean, without getting more specific, it's like if there's something that has a strong capacitance was also diffusing at the same time, you'll get something that's in between. And if you have something that has a very high propensity for homogeneous electron transfer, but it also there's a lot of diffusion happening. Maybe you have less than 45 degrees, less than 0.5. So it's a bit of that mix, if you will, something like that. So I hope that kind of addresses, Isaac, those questions a little bit, and that kind of, I don't know, does my best I can to explain the phenomenon of Warburg and the angle.
Yeah. I was thinking maybe another way to think about it possibly is from the phase angle perspective, which is to say that your phase angle is 45 degrees, which means that if we think about impedance as like voltage over current, frequency dependent, there is an offset. So if you have something that's capacitive, it's like, oh, well, the time it takes to, in a way, like charge the capacitor makes something 90 degrees out of phase with its resulting current. And a resistor has no change, no phase delay. Then diffusion as a process only has a slight offset in some way.
Has a 45-degree offset.
Has a 45-degree offset.
Precisely, yeah.
So it's something that changes the speed, I guess, the way the offset is.
Right.
And to a certain degree, it's like we kind of accept that like capacitors have like 90-degree offset or negative 90-degree offset.
Right.
And resistors have no offset. But like we don't actually think about like, well, why is that the case? And this, well, Warburg is just kind of an in-between thing. I feel like this goes to that. I sent that meme in the chat about the hierarchies of
hierarchies of understanding impedance.
Yeah, and it's like at the very top, it's like the pure physics, like definition of it, and it's like, oh, that gets pretty complicated. Yes. But yeah,
whether you are nobility or peasantry,
yes,
trying to understand
this concept.
Yeah, it does get, it's multi-layered, but yeah, I hope that kind of clarifies things a little bit. So
Yeah. So Shamin Shah is here. Shamin sent me an email earlier with some questions about some of the work that he's doing, and he agreed to allow me to share it over the live stream, as well as talk and discuss it. And I've sent him some emails regarding kind of like answers, if you will, to his questions. But I'll briefly share at least. Make sure that this is showing, because this is just a picture. But he's doing hydrogen, the hydrogen evolution reaction. I believe, and these are different types of like catalysts and stuff like that. And we talked a little bit. He's doing this at about 5 millivolts per second. He's sweeping from a positive potential to a negative potential, and he's inducing the he's basically reducing protons. At least I think that's the mechanism. Reducing protons to hydrogen gas. And one of his main questions is about this offset. Why is there this offset when he's looking at things? And specifically, he has a dashed line around 20 milliamps per square centimeter for the current density. So he's using this 20 microamps, milliamps, sorry, these 20 milliamps as where the overpotential is, as kind of like how he's defining the potential offset between these. Like, oh, this is not as good a catalyst because it's a much more negative potential than this guy to reach the same current value. And so one of his questions, if I can go to it, was, normally you would look at the 10 milliamps per square centimeter as like the point to calculate the overpotential instead of 20 milliamps. And he wants to know if that's okay. I think the absolute values, if you will, might be somewhat problematic because you do want to keep it to that like minus 10. And so I discussed with him, like, and this happens to a lot of people. I see this all the time. Why is there this offset? Why is it the case? Another way to think about this is, why is it the case that at, say, 0 volts, there's current passing in the system? And it's often the case that just because you are at 0 volts versus a reference electrode, it does not mean that there is 0 charge on the electrode, or that the potential, if you will, of the working electrode, or what your molecule is feeling, what the proton is feeling to undergo an electron transfer, is 0 charge. And I can go into more detail about that if that's curious. But the kind of very simple answer to this question is like, oh, well, I want to use this at 10, but nothing starts at 10. You can start at more positive potentials. So Sherman, this is kind of the answer, I would say. One thing that I would recommend trying is, instead of starting at 0.2 versus RHE, why not start at something like 0.5? Or measure the open circuit voltage, right? So the open circuit voltage, or the open circuit potential of your experiment, will tell you at what potential does no current flow. And so you can almost use that in a way, in combination with your RHE, to determine, oh, hey, I need to actually start my experiment here, where there's 0 current. And only in the case of this green one, do you get something with like no current. But ideally, for your catalyst and for looking at the system, you should be able to go a bit more positive in potential. Really figure out where you're getting approximately 0 current, and then sweep the potential negatively. You can still go to your original, like, minus 0.8 or minus 1 volts. You can still sweep, but you get more information that way. And it's much easier to then see and tell, like, okay, at what potential does this guy cross 10 milliamps? Because I think you're really going to want to see, if the literature is using 10 milliamps, I would also recommend using 10 milliamps. in general, especially as as you go to more and more negative potentials, and as you can even see, the slopes of these start to deviate. So this distance here, um, I don't think it's the exact same distance between here and here. So picking voltages to compare different catalysts, I would still stick to the 10 milliamps, mostly because of the literature. But start more positive. Start at a potential where there's no current. So hopefully hopefully that's helpful. I'm going to just check very quickly. So I'm going to stop sharing for a minute. I'm going to just see if you had any other um, questions regarding that. You also, I answered some of your other questions about like when you were doing certain cyclic voltammograms, why was it the case that as you kept sweeping the same voltammogram over and over again, it was changing or the current was very different. And this had to do with the other question that you mentioned, which had to do with electrode activation. So I can talk a little bit about that if can at least talk about that relatively quickly. But electrode activation is, let me just share. And again, of course, let me know if you have any questions. But electrode activation is I guess, a loaded term, and we hear that quite a bit. But the idea is when your electrode, your working electrode, generally speaking, it's glassy carbon, and it's exposed to air when it's not in solution. So it's exposed to air, and air has lots of stuff in it. It's got so much stuff. We're not just breathing pure like CO2 and water and oxygen and nitrogen. It's mostly nitrogen. But there's like volatile organics. Humans emit a ton of sulfur. We have smells. Like anytime you smell something, that's a molecule in the air that you're smelling. So there's tons of this stuff all over the place, and your air is getting onto your electrode. And so the electrode surface, if you will, is functionalized with stuff from the air. And a lot of it might be water, a lot of it might be very benign, but you may have OH groups, because this is carbon, right? Like it's just carbon. What bonds to carbon? Whatever bonds to carbon very easily um, will start to form. You may have carboxylic acid groups. You may just have some other, I don't know, carbon, whatever. You have stuff. This is stuff. And when you put this into your electrochemical system, so instead of it being in air, it's now in your solution. Some of these things are still on the surface, right? So when it moves into solution, some of these things are still on the surface. So the act of doing electrode activation is a way of kind of removing these and making it kind of a clean, but also functionalized so that your work is, so that you have a reproducible electrode surface. So when you do kind of activation or electroactivation with CV, you kind of just sweep the potential, just like kind of back and forth and back and forth. And ideally, like either the current maybe gets a little bit smaller because there's less, like this is the reduction of stuff. This is the oxidation of stuff, random stuff on your CV. And you just keep doing this back and forth until you're really not seeing too many features. When you first start doing this, you may observe a feature that, maybe there's a little bump here, a little bump there. But then the next time you do it, it's like, it's a little smaller. And this guy's also a little bit smaller. And it's a little smaller. And so this is a way, and it's a way electrochemically, of you kind of pre-treating and preparing your surface to have more, to have a clean surface and to know what it is. Now, part of your question was about, do you need to do electroactivation before or after you you put something on the surface. This is, of course, another question. I know it's like you just asked this one about it. And it really depends, because if your group, or if the functional groups are based on like, oh, you need to have OH groups on the surface for your catalyst to stick to the surface, well, then you'd better do something to make sure that the carboxylic acid or C double bond whatevers are off. And if you're preparing this in an alkaline solution, then you mostly have OH groups, but the OH might not displace the carboxylic acid unless you do some pre-treatment. Now, to the question, do you always need to perform it? You might not need to, not all the time. It depends on the nature of the electrochemistry that you're doing. And when you're doing like fundamental electrochemistry with like homogeneous inorganic complexes, polishing is usually good enough. But when you're doing this kind of heterogeneous like catalysis and you're putting something on your surface, and you're concerned about contamination, electrode activation may actually be very important. So you have to play with it a little bit. It depends if it's necessary as part of the pre-treatment. So that is my answer, Shaman. Please let me know if you have further questions or would like additional clarification on anything that I mentioned. But hopefully this answers your questions. Okay.
I think Robert had the next question.
Robert's the next question.
So Robert says, hey, if I'm using CV to characterize a redox enzyme, should I use the CV from the first cycle only, or should I run multiple cycles to see if the signal changes, or would that not be accurate? I don't have a lot of experience working with enzyme electrochemistry, but my hunch would be that you are going to run into a problem compared to, let's say, standard types of electrochemistry experiments with metals or glassy carbon or something like that, where you can do cycling for a lot of times over and over again, and it will often be a good idea. Similarly to what Alex just talked about with the activation, if you do CVs over and over again, it sort of settles into a pattern, and you'll be able to get some curves to characterize or to use as a background or whatever the case may be. Now with enzymes, I do think it's possible or even maybe probable that the enzyme could get deactivated over time or used up, or something could happen. I mean, it's sometimes this is biological material, right? Sometimes enzymes aren't necessarily biological, but that often lends itself to this. And there can be some issues, I think, over time where if you do cycle for a lot, you'll start to lose activity. Now, again, I think part of this is also related to what you're trying to study. So, when you say it would not be accurate, it's like you're trying to characterize the redox enzyme. I mean, I guess that characterization can take the form of a number of things, like its activity, it's like maximum activity or something of that nature, or its stability over time. Those are both ways to characterize something, right? So you might be able to answer both questions by running multiple cycles over some period of time, such that you can characterize and look at what's the best activity this displayed, whether it was the first cycle or the second cycle or the 15th cycle, whatever. And then after how many cycles or time, whatever the metric is, did the cycles and the curves start to look different? And that is also an answer. Well, this the best activity this showed was at this first or second cycle. So a pristine enzyme material, whatever it is, has such and such of an activity and ability to perform with the experiment that I'm looking to do. Meanwhile, after 4,000 cycles, it falls apart, or 200 cycles, whatever the number is, right? I don't think, I think you can sort of, as the expression goes, kill two birds with one stone here. You can do multiple cycles, and then it might be perfectly appropriate to use one of the early cycles to characterize its maximum performance, so to speak, while also getting information about how it dies down or or changes. And then, the other level of characterization, let's say it doesn't totally die or go to nothing, right? But it starts high or something, or even starts low and then gets better, or starts high and gets a little worse and then settles into something. Then another interpretation of that analysis and that characterization is to say that over a long period of time, this is the activity we can expect from this redox enzyme. Initially it shows good or bad performance, but after 100 cycles and then in perpetuity, like for the next 1,000 cycles, for example, it shows this activity, which is either better or worse. But that's also a way to characterize it and say, okay, well, this material or this redox species has this activity like in a very stable manner, right? I think both of those are reasonable methods for your characterization and your analysis. So I hope that kind of helps you think about that in a little bit of a different way, because I don't think that you need to necessarily think of this as an either or, like, oh, it's only the first one, or I should do a bunch of cycles. I think both are appropriate.
Yeah. I think just 2 cents. Sometimes, as you mentioned, like to my earlier point, if there are other things on the electrode that could be giving you signal, you might be able to get it off via the electroactivation thing. So it may be well, I've always observed that the first time you do a CV, it's like you might get all kinds of weird stuff, but then the second time it's like, oh, it's more normalized. It's like I'm getting the same consistent signal. The other things went away. The other thing to worry about with a redox enzyme, if it's stuck on the surface, is that there's a technique called anodic stripping voltammetry, and you may accidentally do that by like stripping the enzyme off your surface, and so you get like one nice big peak, and then it just disappears, and then you never see it again. In that case, the first scan was helpful in telling you some information. But to Neil's point, I think you can collect all of the information, and whatever's really stable is the thing that ultimately, like, that's going to tell you the most information. Okay. Looks like, so that was Robert's question. Did you want to talk about
Joaquin's question? Yeah, I can.
Little circuit.
I was just in our software kind of imitating stuff. So Joaquin, if you're here, please comment here. So Joaquin had a question saying, I have this circuit. And so I think, first of all, with the way you've drawn it, I'm not sure. I want to clarify if what I am thinking you mean. So it's got an R and a Gerischer element and then an R with a CPE. Does this element represent diffusion inside the crystalline structure? I'm doing SOFC, SOEC, using perovskites as electrodes. So first of all, the Gerischer element isn't really a diffusional element. It is used to describe a combination of chemical and electrochemical processes occurring. So in an SOFC, it's an electrochemical system. I don't know what chemical process you'd be using a Gerischer element to describe, but there's a K that comes out of fitting, which is a first order heterogeneous rate constant in the Gerischer when you do the fitting. And so first of all, it seems to me that what you're, I guess it's hard to see. Hang on. Let me find a better way to share this. Let me share my screen. It's a little, I drew the circuit, but you can't really see anything. So let me do this. Tell me if this, you can see. So this is the circuit that I drew. So this is what I assume you drew, like R kind of in parallel with a G and in parallel. So it's like you're imagining a 3-tiered thing. I assume you sort of mean the first R is this like ohmic resistance kind of, it's like ever present. And then what you seem to have indicated was that you have an R and a CPE in series, and the Gerischer is in parallel. Now, first of all, I suppose it's possible. It's a very unusual combination. You don't typically, the Q and the G should be reversed here. The Gerischer would be in series with the resistor, and you'd have sort of your typical RC, RQ in parallel. Randall's Voigt element kind of there, and this is a sort of a Randall's element. So I'm not sure exactly if that's what you mean, if it's this or everything is really supposed to be in parallel. Again, my presumption is to kind of you've reversed the normal order of where the Gerischer or Warburg or whatever would be.
He says G is in series.
G is in series.
RG, R parallel, and the last R in parallel with CPE.
So, all right, hang on. Let me draw a new one. So,
sorry.
So read it. I know I'm kind of using
he says
so R.
I'll show it's R, G, R, and those are in series.
And then R is in.
And then he says an R in parallel with a CPE.
I see. So this is what you tell me, Joaquin, if this is what
I think this is what he has.
So first of all, this right here.
Yeah, he says this is right.
All right. So first of all, having this in parallel, I'm going to put it on the other side. It doesn't matter what order it goes in. So first of all, that is a possibility, right? To have this like this. I'll draw it like this first. Okay. Like this. Hopefully I'm kind of hovering on the screen. That's what you've indicated. There's a paper, not to get too deep in the weeds here, by Mark Orizm, who's like an expert from the University of Florida on impedance, who has talked about the difference between having, it's with respect to Warburg elements, but my presumption is that it will be similar with respect to a Gerischer or anything else. Having this Gerischer by itself or here in series, this is more appropriate. So first of all, my hunch is to say that this is probably a more appropriate representation, putting it in series with the resistor while also in parallel with the Q. So that would be my hunch to do that. So that's just the first quick thing. So I'm just going to kind of do this again. Visually, they actually end up looking somewhat similar, to be honest, whether you have it in series or as you've described it, right? So the pattern should make like almost like a second semicircle if I make the K a certain way. Let me kind of just tinker with this and make it look. So I'll talk about this a little bit. So the first semicircle sort of corresponds to the RQ here, would be representing effectively the charge transfer process. And then the Gerischer element here, which is the second feature on the right side of my Nyquist plot, that is just meant to be more descriptive of, it's kind of like a combination of diffusion and a chemical process. So again, you're sort of stuck, this K, this 25 inverse seconds here. This is basically like a first order heterogeneous rate constant. So whatever this would work out to be would be an indication of a chemical process. And now what's tricky is that if you're trying to describe the diffusion inside your crystalline structure, what I would recommend is not using a Gerischer, but instead using a Warburg short, because this kind of pattern here, let me pull up my other webinar that I already kind of talked about this, is more indicative of a Warburg short finite, which looks like this. So this looks similar to the Gerischer. In fact, the only real difference, generally speaking, is that the angle of this first initial kind of feature is a little bit different. It's a little bit lower for some reason. I don't know exactly what angle it is, but it's not usually 45 degrees. It's a little different for the Gerischer than the Warburg. But the Warburg short is definitionally diffusion, and there's no convoluting factor with respect to the presence of a chemical reaction with the Gerischer element. So if you're talking about using something here to describe the diffusion in a crystalline structure of a fuel cell, which is probably definition, like it's a fixed length, then I would suggest using a Warburg short with the circuit model that you have described, whether the Warburg short is by itself or in the circuit. As I said, I tend to fall on the side now after some recent revelations by Mark Arzum that you want to put it in within the the RCPE. But the Warburg short is a little bit more oxygen reduction reaction. Yeah, you were saying oxygen reduction reaction is it's an electrochemical process. So the heterogeneous rate constant of a chemical process is not applicable in this case. So I think it's possible the use of the Gerischer might not be the best one. I could be wrong, and maybe there's some papers I could read where they use a Gerischer. That might be a perfectly good explanation for that, but I'm not perfectly aware of it, to be honest. And so my suggestion, as far as studying the diffusion, especially through a fixed boundary length of like a crystalline SOFC electrode, would be to use a Warburg short in a similar fashion to what you've described. So that would be my my suggestion to you. And follow up, please, Joaquin. We'll keep our eye on the chat if you have a follow up question or clarification about it. I'm happy to talk about
that. We have a question from Vignier Sony. I asked for a little bit more clarification, but Vignier asks, hello, sir. I want to ask in Bode plot how to calculate electron lifetime and what happened when we get two different values. One is in the lower frequency and the other is in higher frequency. And so, Vignier, I sent a quick message in YouTube just to kind of ask, what do you mean by electron lifetime? That's something I don't know enough about. Also, with regards to Bode plots, so this is an example of a Bode plot, and so you mentioned like you get these like two different values, sort of say. So in a Bode plot, you have frequency on a log axis on the x-axis, and it's a double y-axis plot. So on the left-hand side, you also have like a logarithmic z magnitude. So the magnitude of the impedance, which is just a ratio of the voltage over the potential divided by the current. And then you also have this blue, this other y-axis, the phase angle, which is in blue, and that's just indicative of the phase delay or the phase angle at each frequency. So each kind of like value, each data point in a Bode plot has a z magnitude and a degree, a phase angle associated with a particular frequency. So I'm curious what you mean by like having different values at low and high frequency, because yes, there's a different value for the impedance, the magnitude, in the high frequency region, but there's a different value in the low frequency region. And I guess I don't know enough, so that's just what a Bode plot is, but I'm hoping you can elaborate, like, what do you mean by electron lifetime?
He said, which calculated at 45 degree.
Is that what she's saying?
That's so which
calculated at 45 degree.
I'm trying to. Are you saying that there's 2 points on the Bode plot where 45 degrees is present? That's certainly two different frequencies.
Yeah.
I think I don't know what electron lifetime is.
Yeah.
I don't know what that is.
Yeah, I'm not so sure either what electron lifetime is. There are definitely two frequencies, like where it's like, yeah, it's 45 degrees.
I'm also wondering,
impedance is different.
So the question is how to calculate electron lifetime, and then what happens when we get two different values? I assume you mean of the electron lifetime. So if you're asking how to calculate it, and then you're asking about what happens when you get two different values, how are you calculating it if you're getting two different values? I don't know what this.
Maybe we just don't.
I'm not sure I know what an electron lifetime is. This could just be a terminology thing. This might be something that I know under a different name, or electron lifetime. I'm not sure. It's like I don't know.
Well, I don't know. A quick Google search has this like lifetime in like 6.6 times 10 to the 28 years, which is, I mean, it's like
that is not the same thing.
That's yeah. I don't think that's what you're
No.
talking.
So the frequency, I'm seeing just some snippets here. Let me see. The frequency at which the phase angle reaches its maximum value, calculating the lifetime. Is it like that? Is it more like the time constant, I guess? Longer electron lifetimes, lower peak frequency. I don't think I know. I always have the AI thing, and it's like I don't trust it. I want to know where it came from.
Oh yeah. Okay. So you said EIS, electron lifetime.
Yeah, I'm trying to think about this for a little bit here. Phase angle reaches its maximum value. So in your Bode plot, that would be the bottom of the peak, basically. A longer electron lifetime corresponds to a lower peak frequency. Yeah. A longer time for this seems like a kinetic thing. The time for an electron to be transferred is like a kinetic thing. It's like the speed of electron transfer, kind of. I don't think I know enough about this. Electron lifetime in EIS tau. Yeah, tau. Well, tau is like the time constant. Maybe it's the same thing. Time constant tau. Tau is a time constant as well. That's usually like resistance times capacitance is a time constant when you have a void element or an RC or an RQ.
So is she looking at the? Well, yeah, and right. So the time constant. Right. So it's a time, and it's based on the RC, and it's an RC time constant. So it's the resistance times the capacitance.
If you're getting different time constants or different tau values, it could be you have multiple processes occurring, and so they're each happening at a different speed. Yeah, I think you're asking which one is correct. Basically, it's if you have two different processes occurring at different time constants, different speeds, whether that's electron lifetime or time constant, whatever the right terminology is, then neither is correct. They're both representative of those processes if you have two processes occurring. Like if your Bode plot has two peaks in the phase angle, for instance, that usually indicates two different processes that are occurring. And so each of them will have their own speed, time constant, electron lifetime, whatever the right property is, right? Yeah, the blue color line in your plot. Exactly. So if there's two peaks, like down dips on that Bode plot that Alex showed, then I think that is probably indicating there are two processes and they each have their own electron lifetime or tau, basically. So both are correct is my interpretation of your question. Both are independent processes that occur at their own each speed. And that's pretty normal, especially in impedance. It's almost exactly the point of why impedance is so useful. Because when you have processes that are occurring at the same time, but at different time scales, different speeds, different taus, different electron lifetimes, whatever the right word is, all the same thing essentially, then impedance allows you to observe both of them by changing the frequency. And so when you get different tau values for each peak, they are just showing how each of these processes are occurring at different speeds. And by doing impedance throughout a bunch of different frequencies, you can look at both of them. So it's really powerful, actually. But I think that kind of makes sense. Titania dice sensitized, third generation solar cells. Yeah, honestly, I don't know. That could be as simple as like the
so if you have a frequency though, can't you just can't you take the like inverse of the frequency to get the time?
The inverse of the frequency is the time for one sine wave, but that's not the time constant. Like if you're doing if when you have points at 1 hertz, just to take the simplest example, and that's 1 second. All that means is that it took 1 second for a sine wave to be input to the system.
But in like in the example I showed where there's like one peak where you have a maximum in the Bode plot, or I guess maybe a minimum.
Looks like a minimum, but yeah, whatever.
So minimum, yeah, depending on size. So that is the frequency where you have like the quote highest shift, sort of say. And that's also, you know this, that's not the highest point in the Nyquist plot as well.
No, it doesn't correlate.
Does not correlate. So, but there's a frequency associated with that phase. And is she just asking, okay, the inverse of that frequency is the electron lifetime for that specific process? Because it's an RC, you know, we're talking, that is supposed to be representative of an electron transfer through the, you know, at an interface. But I don't know what this.
I mean, it's just the inverse of the frequency is units of time, but that's irrelevant. It's not.
Well, we're talking about a lifetime in units of time.
No, I understand that, but there's a difference between calculating a time by multiplying resistance and capacitance that dimensionally ends up as time, but is specifically related to those processes through their resistance and their capacitance, and taking the inverse of the frequency that was used to make a measurement that by itself has nothing to do with the experiment. It's just the frequency at which the instrument was probing at that moment in time.
No, but that's the frequency where you got the lowest. Like that's the x-axis, right? It's the frequency where you had the lowest or the peak in the Bode plot.
Yeah.
Right. So it's like, that's just like, oh, the potential in the CV is just like, it's just a potential. It's what we applied, but at a specific potential, you got a peak in your CV. Well, that means something. So in the same way, there's a different frequency where the instrument was doing something, but at this frequency, we got a peak. Is that peak? And maybe it's based on this paper, which I haven't looked up.
I have it here. I'm just glancing.
Yeah, I mean, right now, I guess we're glancing at it. And if the answer is simply a matter of like, oh, take the data point at that point and then do 1 over that, and that gives you a time. I don't know if that's what they're doing. They have tau. Well, I'm just looking at that. They put this like 1 over. Oh yeah, and of course you have to convert, radians, 2 pi, some factor like that.
Yeah, they're still using RC. So the next paragraph after the definition of tau in this paper shows that they're measuring the capacitance of titania from the expression C is equal to tau over R. So there's still it's an RC. It's just an RC. It's just an RC.
Yeah.
So so you're getting you're getting a measurement of R and C. Whether you do it one way or the other is almost irrelevant. So I
guess it's only
the tricky thing too is that
because we usually
let me show this because one of the things that I talked about, which you mentioned, I don't know which one it's in. Randall's embedded. The correlation between the peak, yeah. So there's an interesting thing here just to be aware of here. Right here. So, for instance, the peak frequency is not the peak in the Bode plot.
Correct.
It's the peak in the Nyquist plot, just to be clear.
Yeah.
Right. So one thing to be aware of is that okay. So I understand what you're saying, Alex. Yeah. There is a significance to the frequency, the inverse of the frequency here. So what Vinay, what you're sort of referring to is this: the peak frequency is actually the peak of the semicircle on the Nyquist plot. It actually does not necessarily correlate, and I believe maybe even doesn't possibly correlate, although I don't know. I haven't seen enough examples. It does not correlate with the peak on this Bode plot. You see, this is where the peak frequency actually lines up. It happens to be offset, so it's not the maximum phase angle or minimum, whatever the word you want to use is. It ends up being over here. When you look at the 5 columns of data, but it is the peak of the semicircle on the Nyquist plot. This is just mathematics. I have no other explanation for you other than this is just what mathematics shows us. It's just what happens. It's not here. It's actually over here. It just is. I don't know why. It just is. So to be clear, if you're taking it from the Bode plot in the bottom of the blue peak on the phase angle, you might be wrong off. And now the second is that the tau is equal to that's this right here. This is the same. I'm not calling it tau yet, but you see omega p this is the same thing. Yeah. So this is the expression 1 over whatever. What's the way they write it? It's tau is equal to 1 over 2 pi f.
Yeah.
And so what I have in my slides here, 2 pi f. Omega is 1 over tau because omega. This is frequency, so it's 1 over that. So anyway, this is the same thing. What I'm showing here is the same thing. And the peak frequency is just to be clear is the peak on the Nyquist plot. So just be aware of that. Be careful you don't pick the wrong peak frequency. But then effectively, it just what it allows you to do in the context through which I'm showing it in my slides here is it allows you to calculate the interfacial the capacitance, because that peak frequency is 1 over RC. So this is how you get to your time constant, your tau. And so back to my original point, which one is correct? What you're seeing in my slides right here is where you have one little peak right here, right? Well, if you have 2 peaks, you're going to have 2 time constants and 2 taus and 2 interfacial capacitances. And so the likelihood is that you'll end up having 2 of those. Which one's correct? Well, not both are correct. There can certainly be multiple time constants involved in an electrochemical process. And the interesting thing with this paper is I don't even see a Bode plot. Maybe I see a Nyquist plot. And it looks like they have 2 semicircles on this Nyquist plot. They also don't do it orthonormally, which is very unusual.
And this is nature.
It's nature. I can't believe they don't show oh, there we go. Phase and frequency. They do have that. So you can see on the phase in figure 16 in the paper you mentioned, for instance, like there's a big peak at the beginning of the frequency. Also, the frequency axis is not logarithmic. This paper is committing a lot of faux pas in terms of the electrochemical representation. So I'm quite disappointed. You don't usually put the frequency axis in linear plot here, but in any case, it looks like there's a peak, and then if you were to continue, you might have another peak. If it were logarithmic, it might be easier to see. But there could be multiple ones, and that would lead you to multiple time constants. So anyway, I'm going to kind of leave it there. I think hopefully that kind of addresses that question. But we're all talking about the same thing, and yeah, the interesting part is I just haven't heard electron lifetime as a
yeah, we have to read this in more detail.
No, it's. I think it's similar to. I mean, yeah, obviously in more detail as far as the specifics related to this dye-sensitized solar cell, which I'm not an expert on for sure. But the fundamentals are the same, which is that a time constant is the resistance time, the capacitance. It's also that is related to the inverse peak frequency, but the peak on the Nyquist plot, semicircle basically. So if you're looking just at a Bode plot, you may make a error by assuming that it is equivalent to where the peak is on the Bode plot. That is not correct necessarily. So,
and that means that this paper is probably wrong.
Might be.
It might be wrong
if they're not taking the peak of the Nyquist plot. That is the incorrect peak.
Yeah,
I guess it's possible it could coincide. I don't know. Again, it's just mathematics. Mathematics are that way. I'm not gonna. I've done that in my webinars and shown a little bit, but
their Bode plot
it's not logarithmic. It's a mess.
Well, yes, you're right. It's not logarithmic.
You can't really tell.
And their peak is very
well. Again, the problem is if it was logarithmic, you'd be able to tell where that is because these points are not equally spaced out.
Correct.
So this peak might look normal on a regularly plotted Bode plot, but they did not plot it that way. So
it's also a very interesting peak. It's not like
they inverted the phase angle axis too. You usually plot minus phase angle. That's why it looks like
it looks super weird. Yeah.
So anyway, I hope that kind of helps. Vinay, we kind of talked through it a little bit.
Yeah.
I hope that's somewhat clear. And anyway,
Yeah. Nature.
yeah,
Did I
yeah,
say
yeah.
science? I thought I said
No, it's from
nature.
nature. You said nature.
I said nature.
Is it? It's scientific.
Scientific
But
reports.
it's a nature
It's
paper.
nature.
Yeah, it's a
yes.
nature paper. Yeah.
It's a nature paper.
So yeah, it's surprising to see impedance data plotted this way. I don't know if this is common in solar cell publications. Admittedly,
Yeah.
it's not my
But
area of expertise, but I disagree with how that is presented. I don't know how useful that. It's not conventional. Let's just say. I guess we'll leave it at that.
Yeah.
Joaquin has another question. Last one.
Yeah.
What do you consider to be the main differences between a liquid-solid interface and a solid-gas interface from a physical perspective of the circuit elements used to model? That's a great question. I don't know how solid-gas interfaces are modeled. Well, that's not entirely true. There are similarities. I think one of them would be probably the diffusion. I suppose diffusional properties are probably a lot faster in gas than in liquid. That seems obvious. Is that correct? I mean, right?
Yeah. The diffusion. I mean, yeah. I guess
stuff moves a lot quicker. In gas
stuff
form
moves a lot quicker that way. I'm just thinking
but so in some sense, the answer to your question is there isn't necessarily a difference in terms of the circuit elements that are used to model. And so the thing that comes to mind is like a fuel cell, which has kind of both interfaces present in a lot of cases, where you'll have gas flowing on the backside of the gas diffusion layer. So you're doing an SOFC. I assume you have. I think that works with oxygen gas on one side. I forget which, and oxygen is ripped apart into radicals. SOFC. It's not my fuel cell of great expertise, but I do know it's oxygen is yeah. From a physical perspective, can one element model both systems? Yeah, I do think so. I think you'll probably get different values for sure. And again, one of those might be that the diffusional measurement, for example, that you get from the Warburg, let's just say you fit a Warburg short because you have that finite element like I talked about before. You could, in theory, fit it to both types of interfaces. And I guess my expectation is that you would get a very different value for the diffusion coefficient or for the W or for whatever the fitted elements, right, that you get are between the liquid solid and the gas solid interfaces. But they're still processes that are occurring that are similar in a similar way. If a liquid, an active species in a liquid form or the gas form is close enough to the electrode, it should be measurable electrochemically, whether in gas form or in liquid form. And the processes are probably going to be similar, especially if there's a charge transfer. Diffusion is where it gets a little bit more difficult, I guess, again, because I would suspect the speeds and the rate of diffusion is going to be very different. Whereas with liquid, something's diffusing in liquid, and then it's in the inner Helmholtz plane or whatever. And then when it moves too far away, it's sort of not detectable when it's too far away or whatever. With gas, it's like it could probably move to be that too far away a lot faster. Like it just quickly gets flushed away. It's gas, right?
Yeah, under some pressure as well.
Yeah, or flow rate or whatever the case may be. So I do suspect that you can use the same circuit models to fit, but you'll probably get different. I would expect to get different results fitting wise, and similarly with the resistances. I suppose probably gas phase would be easier. Not necessarily, I guess. I don't know. I'm sort of guessing here, but maybe you get different values for the charge transfer resistance and things like that. But it's still a resistor, whether it's liquid or gas. Maybe the value is just a little different. So anyway, I hope that's talking through it a little bit there, Joaquin. So yeah. That's my impression.
So we just had a new question from Sean. Sean is asking, "Hi guys, Sean here, USA. I'm a chemist, but not electrochemist, and I am tasked with investigating selective production of chlorine and oxygen for a chlor-alkali cell, but using a mixed salt. Need general info on overpotential studies. Let's see. Let's see.
Let me take a look at something real quick here.
Chlor-alkali. Yeah, because
So
I was under the impression the chlor-alkali
producing chlorine and oxygen gas.
Like to make bleach is one of the biggest electrochemical.
Yeah, bleach is a pretty
systems.
But that's also bleach is sodium hypochlorite. It's not chlorine gas.
Yeah.
Right. Which
Yeah.
So one of the dangers of bleach is that it releases chlorine gas if you mix it with other household chemicals and aren't careful or whatever.
Mm-hmm.
So I'm just trying to look up the potential really quick here. Chlorine gas. Where's chlorine gas? Chlorine gas
for like
right.
the reduction.
Yeah. So all right, oxygen. So okay, I'm gonna share. Yeah. This is a page I like to show a lot here.
Yeah, good old Wikipedia.
Yeah, good old Wikipedia standard potential pages. So first of all, as it relates to overpotential studies and things like that, the main things to be aware of, Sean, are the potentials at which these occur. So I don't know a ton about mixed metal salts and chlor-alkali processes. Precisely, I don't. Unfortunately, I haven't done that kind of thing, but I can talk about it in a general sense, as you mentioned, from an electrochemical perspective. So the production of oxygen gas is going to. This isn't the right one. This is acidic. You're doing alkaline. Bear with me here. ORR alkaline.
You can still.
I'm just gonna
still at least mention that the chlorine gas.
It's the same potential. It's just the alkaline pathway here. I'll say. I'm going to share a different tab really quickly.
Okay.
Replace with this tab where I've searched for this rather than write it out. I'm going to just cheat and show it here. Okay.
Yeah.
So this is the oxygen reduction reaction. Ugh, I can't see. I just sort of saved this one screenshot here. Maybe it's in an image. I just want to kind of bring it up. This table here might have it.
Is it the first? Oh. I was going to say it's the first.
It went away. It went. Oh, here it is. Yeah. I'm just trying to
make it.
It's all like fuzzy and blurry. Whatever. You can probably see some of these. Hopefully you can see some of these. pH greater than 7. This is a direct 4 electron oxygen. So this is the oxygen reduction reaction. Oxygen plus 2 hydrogen plus 4 electrons gives you 4 OH. The standard potential is the same whether it's an acid or base. I just wanted to show you the alkaline one, so I recognize you're doing an alkaline process. In any case, back to the other tab, so I can show you the chlorine one as well. The point is, standard potential page. All right, I'm just going to talk through this a little bit and then try to think through some stuff. This is the reaction here, right? The reactant is oxygen. The product is water. In your case, it's alkaline. It's hydroxide, right? But again, just ignoring that for a moment. Now, that has a standard potential of 1.2 to 1.23, basically. Volts. This is a very, very well-known reaction, the oxygen reduction reaction. Going the other way, it's called the oxygen evolution reaction. That is what you are interested in. So when you're talking about generating oxygen gas or chlorine gas, it's going the other direction. So this is the oxygen evolution reaction. Now, this standard potential is written with respect to it as a reduction. What it means is that if the potential is less than this standard potential, it will operate as a reduction. So conversely, if the potential is greater than 1.23, it will go as an oxidation, which means it will go from right to left, which means the first thing to think about if you are having to produce oxygen gas, as in the oxygen evolution reaction, as in doing this reaction from right to left, going from H2O to O2, which is producing gas, you need to be at a potential higher than 1.229.
Or it needs to be negative.
No, positive. It needs to be above that.
It needs to be above that?
Yeah, this is a reduction. We're going higher than that. It's an oxidation reaction. We want to go the other way.
Oh, he's taking...
He has some salts, I guess. I don't know.
He's taking OH minus.
Yeah, and producing oxygen gas.
And then of course this is all related to SHE.
Yeah, I'll talk about the shift in just a minute. Yeah, you might be. Yeah, so that's the first thing. So I'm sort of going on a basic level here.
Yeah.
Hopefully it's helpful to you. Cells are separated. I'm just reading comments a little more. Cells are separated by anion or cation passing membranes. Anode side is neutral pH. At first, when O2 is produced, it goes acidic. Yes, you have a weird cell. One side's acidic, one's alkaline.
Okay.
In any case, this is versus like SHE at pH 7. If you have a potential that's greater than this on the side producing oxygen, that will happen. Chlorine here is the same principle. If you have Cl minus ions and you go to a potential higher than 1.36 versus SHE or NHE or whatever, you will produce, in theory, chlorine gas and electrons. You will oxidize chloride, If you had a potential higher than 1.36, you will oxidize chloride ions and produce chlorine gas. So, by that logic, in general, it depends if the electrocatalyst is good at doing these processes or not. It depends on the amount of ions in solution. It depends on a lot of stuff, right? But in general, if you have, and again, I'm also assuming these are on the same side. I don't know, maybe one's on one side, one's on the other side. I don't know. If you have a electrode at a higher potential than 1.36, it could in theory do both of these reactions, right? Because 1.36 is already higher than 1.229. And so that's just like fundamental electrochemistry. If you're at a potential that is lower than the standard potential, the reduction happens. If you're at a potential that's higher than the standard potential, the oxidation happens. And so the oxidation of both of these reactions is what's producing. Oh, geez, Louise. We're going all over the place. The oxidation reaction on both of these is what produces oxygen gas or chlorine gas. And so the potentials of interest are here. Now, that's the first part of it, right? The second part is all the stuff about pH. So the reality is that the standard potential that I just showed you, 1.36 or 1.23, it shifts by minus 60 millivolts per pH unit, which means as you go from pH 7 to pH 14, you go up in pH, the standard potential goes down by 60 millivolts per pH unit. Was that 420? 6 times 4 is 42. 7 times 6 is 42. So 420. So 400 millivolts. So at highly alkaline electrolyte, the standard potential of the oxygen or the chlorine gas reactions is going to be about 400 millivolts less than the numbers I just showed you. And so that's where your standard will be. Now, if you have a reference electrode, it even moves based on your reference electrode. Potential is a pain in the butt. It moves all over the place. But as long as you know where your reference is, what pH you're at and everything, then you can do stuff like that. Now, you said the O2 is produced, it goes acidic. So if the pH is going down, it goes the other way. The standard potential changes. So that's talking through in a very general sense, I think. It'll get a little more complicated if you have to talk about one is being generated on one side and one's being generated on the other side, because then you have a cell potential that is the difference of the cathode and the anode. And then you have to make sure that cell potential is large enough such that the potentials at either side are big enough to make things happen. I don't know if you can produce chlorine on one side and oxygen on the other, because they're both oxidation reactions. So it doesn't seem possible. One has to be a reduction.
Yeah.
So I don't know that they could both be, maybe they're both produced on the same side. And so the reality is you just need the potential that's big enough that it overcomes the energy of both of those, right? So if you're producing chloride, you could in theory still produce oxygen. The struggle could be, let's just say that the oxygen happens at a lower potential than the chlorine. So you'll probably have always a higher overpotential for the oxygen than the chlorine, because that one happens first. You're always going to have more driving force for the oxygen production than the chlorine production. But I don't know 100%, but that might depend on the electrocatalyst, how good it is, stuff like that. I'm going to leave it there. Sean, comment if you need more of a follow-up. I tried to be somewhat general. I can talk a little more specifically about fuel cells or things like that, construction, but I kind of tried to take it to basic electrochemistry to hopefully answer your question, as you said, some general info there on overpotential studies. Follow up if you want to, if you need me to talk about it a little bit more. We'll move on for now.
Let's see. Garda Viewer has a question. He asks, why can't the Butler-Volmer equation tell you about mass transport at low overpotentials, but only at high potentials? The Butler-Volmer equation doesn't mention anything about mass transport
at any potential.
It's an expression purely about the kinetics of an electron transfer reaction. So if you look at the Butler-Volmer equation, which I'll bring up in a quick minute. Let's see. So if you look at the Butler-Volmer equation, this big mess here.
Big mess.
Yeah, because we like to take this part and just call it I,
I0.
I0.
But Alex hates I0.
I like to write the whole thing.
Alex hates I0, so he won't ever write it.
Exactly. Well, hate's a strong word, like to really not like exchange current density that much,
Hate it so much.
It had, exchange current density had to like agree to go out with me on a date and then stand me up and then like
you'd really
and then like leave me just like a text message just saying like, oh, I'm not gonna see
and it waits
you.
a week before even letting you know that it was like, yeah, I'm not interested in a second date.
If that's the case, I'm like,
then you
wow, I really hate
I'm done
exchange current density.
Current.
Always coming back to K naught because K naught answers my text messages and it's very low.
It's
anyway,
nice.
Sorry, this is a side tangent. So remember, mass transport just has to do with like these things. It's just how does a molecule get from point A to point B? It can move through random diffusion. It can move through migration, the change in a potential and electric field, and it can change from convection, physically moving, stirring solution. This is all the flux described by the Nernst-Planck relationship is all about mass transport. But none of these terms, only like concentration is in here, but that's about it. Like we only get the concentration from the Nernst-Planck relationship, but this expression only has to do with the kinetics, the heterogeneous rate constant, and its relationship with how does the potential, or more specifically the overpotential, change, multiplied by, of course, the concentration of the species in solution, and what does that result in terms of the current that we measure. So regardless if this is high or low, this expression does not tell you about mass transport. There's no mass transport terms in the Butler-Volmer equation. So that's your first question, and of course, if you need some follow up, more explanation, we can do that. He also has another question, which is about. Let's talk about industry. What big companies are doing electrochemical synthesis, i.e., not batteries, on large scale? I know Enos is one. I'm really not so sure. I don't. Do you?
Chemical synthesis.
I mean, we just talked about the chlor-alkali.
Yeah.
The things that use bleach, right? Like to make bleach is like the biggest industrial scale electrochemical reaction. There's plating reactions. It's not synthesis. None of these I would say are synthesis reactions. I mean, you're making something, but I don't know if it's like not like an organic synthesis reaction, sort of say. That's on the large scale.
Yeah,
I don't really know.
I don't know. I mean, honestly, like, look, our company has customers, in industry. I'm not really gonna divulge our customer information.
Oh yeah,
right. For most probably some of our industrial customers would fall into that category, I would guess. Maybe,
it's
but
just the use of synthesis in particular.
Yeah,
we're gonna have to talk about our customers.
I'm not going. Obviously, I'm not going to do that. But yeah,
most of our customers are academic researchers.
Yeah, no,
they're not making anything.
Yeah, well, they're making.
Well, they're making stuff.
They're making confusion for themselves as they try to get PhDs.
Yeah.
No, but I mean, look, we do have mostly academic customers and stuff, but we sell to some industries. For example, the corrosion industry and the energy industry. Mm-hmm. That's not a synthesis, right? But I'm just saying we sell to companies, not just like the university of wherever, as well. And I suppose, like, the thing is, also from our perspective, like we work at a company that makes electrochemistry research products. It's not always our business, as strange as it may sound, I guess, that we sell to some company in California and they want electrochemistry products or something, right? Mm-hmm. We don't always get to know or even are able to know like what they're doing. Like they might have, a lot of times that, especially, this happens a lot. I don't know. It's happened to me for sure. It's probably happened to you. We're doing technical assistance and someone's like, oh, I'm getting bad results or this or that, or can you help me? What do I do with this? How do I set this thing up? So it's not even always that it's the equipment's wrong. It's whatever. And it's like, oh, well, what's your system? And they're like, I can't tell you, right? Like that happens for sure. So there's very probably a lot of companies, even locally in America and certainly internationally, that are doing processes, whether it's electrosynthesis or anything else. And it's just hard to know sometimes because a lot of times they're working on, they're protecting their intellectual property and they're working on, one example that comes to mind, which there are some companies, I think in the Northwestern United States that are working on like the quote unquote forever chemicals that are in water. PFAS, polyfluoroalkyl, I can't, something sulfon something, anyway,
probably sulfonate somewhere in there.
Yeah, something like that. Anyway, the point is that there's these obviously chemicals in water supplies that are from plastics or other manufacturing processes that some folks are trying to remove, and these are, again, maybe it's not synthesis, you wouldn't classify it as, they're not making something, they're electrochemically breaking down materials that are hard to filter out of water supplies, something like that. And so that's just what I would say. Maybe it's not, again, synthesis, but it's like use of electrochemistry in industry. That's not batteries. And there are some companies that are working on processes like that. Like they have, I've seen one, there was a news report on it. You could probably find it somewhere. I don't remember. It was some time ago, but it was like some company, they have this big mobile, looks like a big trailer. And they like could move it to a water source or like a stream or something, and almost like divert the stream into this thing. It's probably got stacks and fuel cells in it or something, but it's an electrochemical process, and it effectively electrochemically filters out whatever chemicals are bad, something like that. And so there's some companies that are working on stuff like that. I mean, there's certainly other processes of interest that electrochemically are, being studied by a lot of companies there. But sounds like not many household chemicals are being made with electrochemistry except Chlor-alkali process by Ineos. Yeah, maybe. There may be other that would surprise you. To be honest, I don't 100% know. But back to the Chlor-alkali process, because Sean had asked about that. I guess one of the things that was confusing me about it is you were saying that you're making chlorine and oxygen, and when the oxygen's formed, it's making things acidic. I think you're confusing oxygen with hydrogen, and maybe I'm wrong, but the Chlor-alkali process, this is why I think I was, at least even not knowing Chlor-alkali process that well myself. Your explanation was confusing because the production of oxygen and chlorine gas are both oxidation reactions, whereas the production of hydrogen is a reduction reaction. And so this right here, just as one example I picked, is a lot of, images on this. As you said, I searched for Chlor-alkali diagram. It produces chlorine and hydrogen gas. And that makes more sense because, again, chlorine gas, 1.36 volts. Hydrogen is 0. The hydrogen evolution reaction is at 0 volts. So you can put together a cell that produces chlorine on one side and hydrogen on the other, and it will have a cell voltage of 1.36 in theory. Practically it's probably different. But this is just like a standard cell that you can do. And so hydrogen, and that makes more sense as well, that as hydrogen gas is produced, you might end up with a acidic process. Like maybe there's protons that are getting dissociated or something like that. I mean, it's sort of the opposite, but you're producing hydrogen, you're combining protons to make it, but something of that nature maybe is making it more acidic or something like that. I think it would make it more, I feel like it should make it more alkaline because you're removing protons, leaving behind hydroxide. But in any case,
it looks like in the picture it is forming hydroxide ions, but they're just diffusing through this barrier.
Oh, okay. So maybe
might be
maybe the loss of the hydroxyl to the other side makes it a little more acidic. So something like that.
Something
this isn't my
we don't know.
system of expertise, but I do understand it on some fundamental level because I know how fuel cells work a little bit. So anyway, just as a point of clarification, all of what I talked about is probably still a good general overview, but you probably will not be thinking about the production of oxygen gas. I don't think that's, I think you meant hydrogen. I think maybe you just meant hydrogen, you wrote oxygen, something like that. Is my guess. Nope. Cl2. Oh, okay. I see what you mean. Hydrogen on one side, and then either
and
Cl2 or oxygen. Yeah. Okay. So
Oh.
what I talked about is still the case. Yeah. Right.
Yeah, makes so much more sense now.
Yeah. They're going to be competing basically because the potential
Yeah.
for chlorine gas is high enough such that it can also produce oxygen gas because of the
Yeah.
potential thing that I talked about. 1.36 is higher than 1.2. So you, by definition, when you're producing a chlorine gas, can also produce oxygen.
Yeah.
And then hydrogen. I think what I was missing, Sean, was that the hydrogen's on the other side. Your explanation
Yeah.
made me think that oxygen was on one side and chlorine's on the other. Those are both oxidation reactions. That doesn't make a cell. It doesn't work.
Yeah.
So I get it now with the hydrogen on one
Now
side.
it
That
makes
was the
sense.
missing piece for me in my brain. basically. So okay, so I understand.
That's good.
Okay, so I think was it Yeswant here?
Yeah, Yeswant has a question. It's kind of a lot of things.
Yeah.
He says, "Sir, can you explain number of electrons, Kurecki-Levitch plot, and mass diffusion and Tafel plot?" Those are all.
That's a lot of things.
That's a lot of things.
So the short. So let me say this. The short answer is yes, but not now.
Yeah.
I have done webinars. They are on our YouTube channel, which
Mhm.
presumably you are on now. So your comment came from YouTube. If you look on our webinars playlist, you'll find a number of instances over the past couple of years where I've done a webinar on RRDE,
Mhm.
Kurecki-Levitch, Tafel analyses. I go into all the detail about the Levitch equation, Kurecki-Levitch equation, Tafel equation, number, and the whole thing. And I show a full calculation in the second part of that. It's a 2-part webinar series. It's simply too much to go over now. It's a full 2-hour webinar, 2 hours plus of webinar, right? So I would encourage you to watch that on our YouTube channel. You have to be a tier 2 member to do so. But what I will do now is just show you the number of electrons. It's the first part of your question. So I'm going to assume it's the most important, which may not be the case. But I'll show you where the number of electrons comes from in the Tafel plot. I'm going to actually share my whole screen and do a presentation. Let me do that. Presentation. I'll go through. These are slides from the webinar, and so I'll at least do you one solid, I guess, and try to do that. Taskbar. Say share my presentation. Here we go. Okay, so then where's the number of electrons come from? Well, first of all, it comes from the Butler-Volmer equation, which comes from the Tafel equation. So again, I'm sort of neglecting Kurecki-Levitch and stuff like that. See the webinar for more details. The Butler-Volmer equation, which is what Alex just showed, except I'm showing it in the correct form with I0. So as a little jab there, just jabbing it in there. Yeah. See, I0 calls me back. That's why I included it in my
I know. I0 likes you.
Exactly. Okay. So in short, with the Butler-Volmer equation, it describes the kinetics, the current response as a function of overpotential, which is this eta, looks like an N. If I have a large enough overpotential in either direction, oxidation or reduction, I can neglect one of these terms. That effectively makes it irreversible. It's about 120 millivolts or greater, makes it roughly irreversible. I can then take effectively half of the Butler-Volmer equation, and that is the Tafel equation. It's just half the Butler-Volmer equation. It is an expression that talks about the kinetics. So we replace I with IK. So this is kinetic current is equal to the exchange current density, which is basically the heterogeneous rate constant, times e to the alpha NF over RT times the overpotential. All we do is solve for the overpotential. So we take the natural log of both sides and we do some rearranging. We get this expression here. This is the Tafel equation. It's just a rearranging of the previous equation. All right. So the overpotential is equal to a function of the log of the kinetic current. This is how you get Tafel plots. You plot overpotential versus log of IK, or the other way around. It doesn't matter. All of the stuff in front of the log of IK is the slope if you consider y equals mx plus b. If we make a linear plot of overpotential versus log of the kinetic current, the slope is the stuff times the y variable, right, which is log of IK. So RT over alpha NF, log of E is just a number. This is like 2.5 or something. So basically RT over alpha NF is the Tafel slope. And we call this B, okay? Now, where does the number of electrons come into play? Well, it is in the denominator of the Tafel slope. So for a typical equation, with 1 electron transfer, N, and a symmetrical energy barrier of 0.5, the Tafel slope is about 120 millivolts per decade, 118, okay? Millivolts per decade. That's a typical Tafel slope. But what people are often doing when they are doing Tafel analysis and Tafel slope analysis is finding Tafel slopes that are different than 120 millivolts per decade and making the assumption that it basically has only to do with the number of electrons, because most of the other variables are not really changing in a typical experiment. So we have R and T. Now, unless you're changing temperature, it's not really changing. R is the ideal gas constant. It's obviously not changing. F is Faraday's constant. It's not changing. Alpha is the symmetry of the energy barrier, which probably is also not changing. Even if it isn't 0.5, it's probably not changing. And then for a lot of cases, we just probably make the assumption that it's symmetrical. It's 0.5. So the only one that really we're studying a lot of the times, we're making the assumption here, is N. And so what we can say as, for example, if we get 60 millivolts per decade for my Tafel slope, well, N is in the denominator. So if N is 2 instead of 120, it's 60. And so one of the explanations that we use from the Tafel slope is that basically the amount different than 120 by what factor it is an explanation for the number of electrons that are transferred. There's some built-in assumptions here I'm going to gloss over for the time being. But effectively, that is how the number of electrons are commonly calculated in a lot of electrochemical literature and in the community. That's a lot of how we do this. Okay, so it's by taking the Tafel slope and assuming N is what's changing. That is a calculation of that there. So that answers the last part of your question. And again, I'll just refer you to my webinar for a more thorough explanation of Levitch, Kentucky-Levitch, and CAFL analyses. And I do them live in that web. Well, it's not live anymore, but in the webinar I do them. So hopefully you'll check that out if you want more information. Let's see. Yeah, Sean, you say, want to produce either chloride or oxygen by manipulating overpotential. That will not strictly be possible because you can just to follow up on that, right? The standard potential, the standard.
Go back to the.
I'm just going to go back to
the table.
I'll go back to my favorite Wikipedia page of all time.
Yeah,
the standard potential page,
because they're very close to each other.
Yeah, the problem you're going to have, Sean, is that overpotential is not really going to be enough by itself to do what you're talking about. And the problem is that you're probably making more oxygen than you want to. I imagine this is something that is fundamentally difficult with the chlor-alkali process, is that how can I make more chlorine gas and stop making oxygen gas? The problem is that once you start making chlorine gas, you're already, 229 minus 360. You're already you're already 130 millivolt overpotential over. So once you get to 1.23 volts, and then you go higher, you're going to start making oxygen gas. It's not really that simple, but let's just pretend it is for a moment, right? It's more of a sliding scale, and you're still producing it at other potentials. But let's just say, for instance, once you get above this number, you start making oxygen gas. Well, you don't start making chlorine gas till you get above this number. And this number is already above that number. So you're already at 130 millivolts of overpotential for the oxygen production once you start producing chlorine. So your overpotential for oxygen production will always be higher than your overpotential for chlorine. I imagine that there are ways that researchers are trying to suppress the production of oxygen compared to the production of chlorine. Probably other things like the specific electrocatalysts probably can play a role. Like some catalysts do oxygen evolution well, some don't. You probably want to pick, like what I just described is in a perfect world, these overpotentials. The reality is that, like, you might pick catalyst A, like platinum is good, for example, and it does the oxygen, it produces oxygen right at 1.23. Great. 1.24, 1.25, whatever, right? Then catalyst B something else, doesn't produce oxygen gas until you get to 1.6. Like it's got a really, really bad overpotential. In your case, it's good because it doesn't produce oxygen. You're trying to not produce oxygen, I'm assuming. So it's a bad catalyst for that, but maybe it's a really good catalyst for chlorine production. So that once you get to 1.4 volts versus NHE, it starts producing chlorine gas. But I'm not at 1.6 yet, so I'm not producing oxygen. I'm making up these numbers. Just keep that in mind, right? But the point of this is that it's more about the catalyst that hopefully is bad at one and good at the other. And that discovery or whatever you want to say, determination does not have anything to do with overpotential. It has to do with other things. Like there's either trial and error, like try platinum, try gold, try ruthenium, try whatever, go down the periodic table and just pick metals and see what makes oxygen evolve, what doesn't, what makes chlorine evolve and what doesn't, and then there's like logic that goes behind when people pick one or the other. Like there's, there's energy considerations, or I don't know, the theoretical determination behind what catalyst will do one reaction or another. And then, ultimately it's the trial and error of experimenting that leads you to see which one does which reaction well and which doesn't, right? But essentially that hopefully answers, addresses that a little bit more. There is that the problem is that with the overpotential, if a catalyst does both equally, the oxygen will always have a higher overpotential because it just fundamentally happens at a lower potential than the chlorine. Okay. I know we have a few questions. Let me see. It's frequency. I can answer this one quickly. Garda viewer says, in EIS spectroscopy, is the impedance typically constant at a particular frequency of voltage current, no matter the circuit? No. Is the impedance typically constant at a particular frequency, no matter the circuit?
If the circuit changes, you'll get a different voltage current value.
Yeah.
Because even if the circuit's the same and the values of the circuit are different, the impedance will change.
It will change. Yeah, it's going to be a function of the voltage and current that are obtained at whatever frequency, and whatever the circuit is there, which is like to say whatever the system is, then that will change the value of the impedance for sure. Yeah, that's not like a static thing.
Yeah.
I know Dooley's he sent you.
I'm trying to get it.
While you're waiting for that, I want to answer at least one of these, because this was one that was made a comment by this person, Alex T98. And so hopefully, Alex, if you're watching this later, I had promised you I'd try to answer this question during our live stream this week. Hopefully you scanned an hour and a half into it or so and found me answering this now for you. But I did want to get to it because I promised I would. He had made a comment on one of our previous videos that said to study the potential at which the hydrogen starts forming. So like hydrogen evolution reaction, I assume. I use LSV with a 3-electrode system. Can I run LSV using a 2-electrode system by just connecting the reference and counter leads together? Also, does the potentiostat always operate by considering the potential between the reference and working electrodes? So I tried to answer this in the comment, and I'll talk through it hopefully relatively quickly. But to the answer your first question, yes, you can do it with a 2-electrode system, but it's probably a bad idea, especially because with respect to the hydrogen evolution reaction, one of the main metrics that you're trying to obtain, and Alex, my colleague Alex here, talked about this earlier in the live stream. If you've watched through this live stream, an hour ago at this point, or half an hour ago, I don't know, time is irrelevant. You showed a customer or a person, right? Shamim had some data wondering about where the overpotential is for 20 milliamps per centimeter squared. Like these are the kinds of metrics that often are done for the hydrogen evolution reaction, which is what potential do I get a certain current density? That's critical because if you have to go to a really big potential, you have to put a lot more energy to get the same amount of current out. You want to produce the same amount of current for a lower energy, which is a lower potential. So when you're doing a 2-electrode system, you don't know what potential it is. You just don't, because if you connect the reference and counter leads to the counter electrode, what potential is the counter electrode at? you just don't know. Is it a platinum wire? Is it a graphite rod? What is that potential, right? The reason we use a reference electrode with a 3-electrode system is because the potential at the reference electrode is known, it's set. And so the reference electrode provides a stable basis for which we can know the potential at the working electrode. And to address your second question, no, the potentiostat does not operate by considering the potential between the reference and working electrodes. It considers the potential between what it measures at the end of the working sense line and the reference line. If the electrodes at the end of the working sense line and the reference line are the working and the reference electrodes, then yes. But if you have a reference electrode and you haven't connected the reference line to it, then it's not doing anything, right? It will always sense the potential difference between the working sense and reference lines. And so if the reference line is connected to the counter electrode, then that is the reference, and it is unknown. And so that could change if the reference electrode is constant. So if there's a change in potential, it's only a result of the working electrode, right? As the working electrode potential changes, the reference electrode stays the same. So we know what the potential is of the working electrode. However, in the 2-electrode system, as the working electrode changes, if the counter electrode changes too, you have this huge potential, but the counter change. We only want to know what the working electrode potential is, because that's the one that's producing hydrogen gas. And so if both of these are moving, reference, counter, and basically counter and working are moving, well, how in the world are you going to know what the working one is? That's the one that you need to know. So if this one is fixed, reference is fixed, as the working one moves, we know exactly where it is because we have a fixed reference point. So there typically would need to be a really good reason to use a 2-electrode system. If, for example, you're just interested in producing hydrogen gas, measuring it with a spectrometer, I don't know, you don't care what potential it produced at, you just want to make a bunch of it, maybe a 2-electrode system is fine. But if you care about the potential at which it's occurring and the metrics related to current density or something like that, then 2-electrode system is going to be probably insufficient to help you characterize that.
I did get Dooley's CV. If we want to take a quick look at this.
Sure.
So he just wants to know if he thinks it's I believe he just wants to know if it's a 2-electron transfer process. Clearly, this is in an inorganic, non-aqueous solvent. He's got ferrocene over here that he centered everything to. And I'm impressed. You got like really
3 volts.
That's impressive.
That's
man.
incredible.
That's really incredible.
That is quite impressive.
Yeah. Yeah, I mean, it looks like around this, this negative 3.407, there's a little bit of a peak here, kind of riding on.
He said he thinks the CV curves are
reversible.
Reversible?
Well, right now it's
Doesn't look reversible to me.
It's showing irreversibility. I mean, I think he's trying to say that this little part here has some reversibility. You did this at 10 millivolts per second. If you just hey, if the system is working, it looks like it's got to be air free for you to do this.
Yeah.
If you just scan, like I would do a scan rate study in this region and see whether or not this starts to grow, because at 10 millivolts per second, you know, if there's like a chemical step that's occurring, so because you have a lot of current here, right? This is very nice, but you're getting very little current on the return. And then you're also getting a little bit of current on this return as well. I think if you went at faster scan rates, there may be a chemical step that's occurring in this reaction, or you're forming some kind of non-stable radical that
if it's like an EC
quickly.
And you're scanning really slowly, it's probably eating it up, right?
Yeah.
So if you try scanning faster, it's a good.
Yeah. So if you did, so let me just show you quickly. So if I were to simulate, say,
does this take into account the speed thing?
Yeah. So if you had, so you're actually, so what you're interested in, Dooley, is this. You have a 2-electron transfer process. We're just going to make up some numbers here, and they're all nice and negative. So we're going to go, let's just say one's at negative 400 and the other one's at negative, and actually yours.
-3 points of that. We don't have to go that crazy.
Well, yeah. I'm just saying relatively. Yeah, we don't
Yeah,
have to go all the way to like -3 volts and all that, but the relative difference is like 200 millivolts between one and the other.
Someone said that it might have electrolyzed the solvent at 3 volts. I don't know. Maybe that's solvent decomposition way back there. I have no idea.
Yeah, but he's got the thing is he's got 2 voltammograms. Let me go back.
Yeah, the orange one doesn't go as low as the blue one, so maybe the second peak in the blue one is a bit of electrolyte decomposition. I have no idea.
Because
I'm just saying,
I don't disagree that there could be some decomposition, but at the same time, like this orange one,
yeah, it's not
is
too
clean.
crazy. Yeah, you would think the orange one would dip a lot more. Like, okay,
Yes.
it dips at the end, like 3.25, 3.3.
Barely.
So maybe some part of the second peak 3.4 you wrote or whatever, maybe that is a little bit of decomposition. But yeah, I agree with you, Alex. I think it's possible there's some, but it's the lack of a massive decrease in the orange curve suggests that it's not a tremendous amount of electrolyte decomposition.
Yeah. And getting this far out, it's very difficult.
It's quite impressive.
I was just gonna say really
to derail everything.
kind of quickly. But and I don't know enough about the solvent. Yeah, the orange line is blank.
Yeah.
So if you had 2 electron transfer process and we added a
no analyte, but there's solvent, Dooley. So the point was that the solvent's not ripping apart. So I think you're good.
So if we have B goes to D, right, as a chemical step, and this chemical step, right now, let's just say it's they're the same. The reverse. I'm just kind of making these up, but depending on this, right now this is very fast. But if I made this a little bit slower, I'm gonna play around with these a little bit, and then we're just gonna do the voltammogram from 0. So these are both reductions, which is what you're doing. And so if we start at say 0 and we go to minus, let's just go a little bit further so we have a nice potential window. Actually we do need to go back, and then we just go back to here. So if and then let's see if is there any other setting I'm missing. I can't, hold on. So I think that's okay. Oh, I need to get let's just give it the same diffusion coefficient for now. All right. So if I simulate this for now, so this is like what you would see. And
perfectly reversible, yeah.
So this is perfectly ideally reversible. And if this reaction starts to increase, like if this is very fast, like the forward going from B to D, and I simulate it, I start to get these like, oh, it's here, but I don't get as much here. There's still plenty of B because I've scanned all the way here, but then there's very little coming back on the reverse scan. So some experiments that you can do is just changing your potential window. Like don't scan all the way. Just scan between, like in this case, I would only scan between like 0 to like maybe minus 500, for example. And then like just simulate that. And then like in this case, I have a very fast electron transfer going on here. So let's see if I simulate that, get a little bit better. But here, where you change the scan rate, that's going to be the thing that you'll start to notice these big differences as you go to like faster and faster scan rates. So that's one thing I think you should kind of take a look at, is how does this voltammogram change as you change the scan rate. That will tell you a lot more information about, and changing the potential window, the potential range. Those things are going to start telling you a little bit more information about your system, and about whether it's like 2 electron transfer, is it reversible, irreversible. If you're a non-aqueous solvent, make sure you don't have any minimize IR, have IR compensation turned off, or not turned off, turned on. Make sure that you're compensating for any solution resistance. It looks like your ferrocene looks fine. I'm just kind of eyeballing it, but yeah, that's kind of my take on it. So hopefully it's helpful. I see there's a lot of comments
Yeah, they were just talking about some of the
like degassing and
some of the nuts and bolts, I guess you'd say.
oh, he's doing this in THF. Oh,
Yeah.
wow.
THF
Jeez.
has a really, really huge window, so that makes sense why you're getting all of that.
Okay.
I think Garda Viewer had also a follow-up. You meant to ask, is the impedance typically constant at a particular frequency of voltage current?
I think isn't this the same answer? It's the impedance typically constant at a particular,
like for the same system?
If it's for the same system, then yes. Like if you did EIS at a particular frequency, you would get a dot on your Nyquist plot, and you would keep getting that same dot.
So
ideally,
if it isn't, it's not impedance.
Correct. Yeah.
If the answer is no, then it's not impedance. It violates the principles of, I guess.
Stability. Yeah.
So for something to be impedance, it has to be linear, causal, and stable. Causality is not a problem, but linearity possibly, and stability, right?
Yeah.
If as you have a particular voltage and current set at one frequency, if the impedance is changing, well, then it's not constant, it's not stable, and so it wouldn't even be technically considered impedance any longer. So the answer is yes, if it is actually proper impedance, I believe. That would be my impression.
Yeah. Yeah.
So yeah. So there you go. And Sean had said, yeah, so right. Other than chemical analysis, how could you determine if it's chlorine or oxygen? It's a great question. It smells, yeah.
Yeah, I mean, light it on fire.
Yeah, well, he said other than chemical analysis. I mean, if you have a gas analyzer, maybe that falls under chemical analysis. Is that physical analysis or chemical? Like mass spec or gas chromatographs or something like that is a way to determine.
Yeah. To know for sure.
I mean, the only other possibility would be some kind of electrochemical detection, which is another similar to what I talked about before. It's like if there is a catalyst that has selectivity towards like reducing chlorine gas or reducing oxygen, which we know a lot of oxygen reduction catalysts, but like one and not the other, you can use it as a detector, for example, like have another electrode somewhere that is set to a reducing potential. Like one possibility is because you have that 130 millivolt difference of potential between oxygen and chlorine reactions, you could in theory try something where you like hold a potential that's between 1.36 and 1.23, and that is above the oxygen potential but below the chlorine. So in theory, a perfect catalyst or a capable catalyst would be able to reduce chlorine that it detects but not oxygen, because it's above the oxygen potential. So it would not be able to reduce oxygen. It's too high, but it is underneath, lower than the chlorine reduction. And so you could, in theory, be reduced, like you're producing chlorine and then you're reducing it back again. Like you're just going in a cycle, but you're using it as a way to collect.
Yeah, it's like an RD experiment.
It's like an RD experiment, I know.
Yeah.
Except it's in a different, the Chlor-alkali thing looks like a fuel cell. So you'd have to have a separate, you can maybe do this with a ring disc electrode though, in a separate kind of a setup where you generate chlorine gas and maybe oxygen gas too. And then on the other electrode, you hold it at a potential that would reduce the chlorine gas back to chloride, but not oxygen. And so that might be a way to use overpotential as a way to detect it afterwards. Could work. Let's see. Reading about impedance and teaching yourself. I thought impedance should be constant to a particular frequency too. Yep, should be for your system. And if it isn't, it is not impedance. So there you go. Let's see. Did we get to everything? Oh, there's a MP Sharma had a question. How to get good CV for the battery materials? What scan rate should be good? Very, very slowly, my friend. Scan very slowly if you're doing CVs on battery materials, like 0.1 millivolts per second or slower. Painfully slow, like so slow that you want to quit doing science. So slow that you decide to go sell pizzas instead of do electrochemistry. So slow that you set it and you come back a day later and it's still not done. That's a little bit, maybe not that slow, but consider that doing a cyclic voltammogram on a battery material is effectively sweeping the potential across its entire charge-discharge platform. its entire charge-discharge window, right? That's what the voltage is. The lowest voltage to the highest voltage. On a battery electrode is like charge from 0 to 100% state of charge. Now, most battery experiments don't charge up and discharge that quickly. 1C means 1 hour. So if you're going over 1 volt in 1 hour, right, that is 1,000 millivolts divided by 3,600 seconds is 0.3 millivolts per second. And even that might be fast, right? You're doing CV because you're trying to study the potentials at which your redox reactions are happening, your SEI is forming, all that stuff. That's perfectly fine. But, if it's 1 volt span and you do 0.3 millivolt faster than 0.2, 0.3 millivolts per second, you're effectively charging it up faster than 1C. And even that might be fast. You might want to be at 0.5 C or C over 3 or C over 5, whatever. The point is, if you scan at 10 millivolts per second, it's like charging up your battery really fast. It's probably not advisable in general, right? It's not really comparable to what it's being done in a battery. So generally speaking, it's a very, very slow scan rate.
So I got, Julie's asked me to take a look at his other, he has another one, which I did receive.
Let me check this real quick. So Sean, a separate cell in the headspace, possibly. Divert the gas somewhere else into a different cell. You could, if you have space in the cell, you can add another set of electrodes in that chlorine compartment with like a second potentiostat. It's a bit of a pain. I mean, might not work so well. Something like that. Yeah, very possibly. But if you can divert all of the gas being produced on the chlorine side somewhere else, you could do what I talked about. It's possible. Chemically easy. NaOH captures chlorine. Oh, okay, that's interesting. Yeah, so that might work. But electrochemically possible, I guess, in theory would work with the method I talked about. Having a potential in between the two will reduce one and not the other. So anyway. Oh, Isaac was away having food. Yeah. I'm envious of having food, but yes.
Oh,
I'm glad
okay.
that you I'm glad I was able to answer that for you. You had the chronologically first question, so we had to answer it for you. So yeah,
food's good.
I appreciate it.
Sorry,
do you want to get to Dooley's thing?
I'll just get to Dooley's thing really quickly. Oh shoot, I forgot which. I think it's this one. Here we go. So this is at 50 millivolts per second. And so also anybody here, like you can also send us data and we're happy to look at it. So in this case, this looks way more like much more peak-like. And I would say like, okay, this is definitely much more like solvent breakdown kind of stuff. It really does
end, for sure.
Yeah, this definitely looks much more well resolved than at the 10 millivolt scan rate. Hard to tell with this. I think this is maybe slightly more pronounced, but of course it's somewhat convoluted with solvent, possibly solvent breakdown when you're doing the oxidation. This does come back. I would be curious to see what happens if you just did a scan from like here to here. Like, don't go to this region. Like, just go here and like, does this change at all? It doesn't feel like it would. I feel like it's hard to tell whether the formation of the second electron transfer, which may be irreversible, is preventing the formation of or observing any reversibility in your first electron transfer of your molecule. So that's kind of my like 2 cents, because this is actually a little bit smaller than the previous one. But yeah, it definitely looks like at least 2 irreversible electron transfers. I'd say you got that. Definitely got that.
Yes. And then finally some solvent ripping apart.
Yeah. And then some solvent ripping apart. I think that's all the time we have.
Yeah, we're sort of at time here. And unfortunately, Claire had a question that I had said too about IR compensation. I think Claire M, you had asked about IR compensation and during or after the experiments, and what's the difference? And we have this other question from Sanjeev that we've been trying to get to for like 3 weeks. And it's been a lot of questions, which we appreciate. And sometimes it makes it hard to get to everybody's questions here. So,
Mm-hmm.
Claire, I do apologize. We'll have to get to it next week at this point. So we'll have to sort of leave it there for now, unfortunately.
Mm-hmm.
But yeah, I guess we'll wrap it here. We're sort of at time. So yeah, apologies for that. There's an IR conversation. I did leave a comment on our YouTube channel. I think when you left a question about IR compensation, you can do IR compensation during and after a scan. And anyway, I can show you how to do it. And unfortunately, I don't have time now. So again, I have it saved. I'll try to answer it first next time. As these things do happen, we get so many questions and it takes a while to answer them. So in any case, appreciate everybody's time and attention. Appreciate your questions. Appreciate the engagement. And I hope everybody has a great rest of their Friday and weekend. And take care, everybody.
All right. See ya.